Hey guys, today we're going to build off of last time and talk about independent events. So our last video was about conditional probabilities. That is, the probability that an event A occurs given that an event B, we know an event B has occurred. So how did we define this? Well, we know that B must have occurred, so we want to scale everything so that B occurs with probability 1. And then the only way that A can occur, if B must have occurred, is that if both of them occurred. So if we know that B has occurred, this part has to be true, and then the only way that A can occur is if A and B both happen. So this was our definition of conditional probabilities, and it's well motivated. Right? It's kind of an intuitive meaning. So what do you think we mean by independence? Let's think about this intuitively. So intuitively, A is independent of B if the probability of A given B, so telling us that B happened, if A is completely independent of B, telling us B happened is really not very helpful, right? It shouldn't tell us anything. So knowing that B happened doesn't change the probability, it's still just the probability that A happens. Right, that's like saying if I flip a coin 3 times and I tell you the first flip was a heads, what do you guess the third flip was? If it's really a fair coin, that information about the first flip doesn't help you at all. So the third flip, the probability it's heads is still a half. And so that's the idea here. So given something about B, if A is independent of B, it doesn't matter what B was. The probability of A given B is just the probability of A. But now then, let's take these two things together. So here's kind of an intuitive way to think about independence. And here was our definition of dependent, or conditional probabilities. And let's put the two together and do the algebra. So substituting in here, we have the probability of A intersect B divided by the probability of B is equal to the probability of A. And so that implies then that the probability of A intersect B is equal to the probability of A times the probability of B. So this is what we're going to take as our definition, the simple formula here. But the reason we come up with this definition for independent events is because it follows from these two things that just make sense intuitively. This should be the definition of a conditional probability. This would be the probability of A if we already know B happens. But this should happen if A is independent of B. And then putting those two intuitive ideas together, we get this definition of independence. So sometimes the definition of independence is not so clear, but that's the reasoning behind it. So let me write that down, the definition. A is independent of B if the probability of A intersect B equals the probability of A times the probability of B. So whenever I went to write down this definition, I began with the probability of A given B. And that's why I'm saying A is independent of B. The way I had it written, the order mattered. But notice here in the definition, the order doesn't matter. There's no reason I couldn't just swap the roles of A and B. It would be the same equation if I changed their names. So in fact, let's divide by A on both sides. So if A is independent of B, the probability of A intersect B divided by the probability of A equals the probability of B. And this just tells us then that the probability of B given A equals the probability of B. So notice that if A is independent of B, then telling us whether or not A happens also doesn't tell us anything about whether or not B occurs. So we get the same intuitive idea about B, and it follows the same definition. So B is independent of A. So notice that independence, it's in fact a relation on the subsets of omega. And so you might ask, is this relation transitive, reflexive, symmetric? What kind of properties does it have? What other relations is it similar to? And one thing we see is that this relation is symmetric. If A is independent of B, then so is B is independent of A. And because it's symmetric, we usually just say A and B are independent. It's because the order doesn't matter. We don't have to say A is independent of B necessarily. I mean, we sometimes use that. But it's also fine to just say A and B are independent events. So that's our definition of independence. And this is a basic property, that if A is independent of B, we can flip that around and say B is also independent of A. I mean, that idea makes sense. But of course, whenever we define something mathematically, we have to check the properties mathematically. So now let's say we have three events, A, B, and C. You might think for a second, what does it mean for A, B, and C to be independent of one another? So A, B, and C are independent if, and here it turns out there's actually four things that have to happen with three events. So it turns out that pairwise, each of these has to be independent. The probability of A and B equals the probability of A times the probability of B. In other words, A and B are independent of each other. Also, A and C have to be independent. The probability of A and C is the probability of A times the probability of C. And B and C must be independent. So the probability of B and C is the probability of B times the probability of C. So any two of these are independent of one another. And finally, the probability of all of them happening, the probability that A, B, and C all occur, is the probability of A times the probability of B times the probability of C. Now, this isn't something I derived, this isn't some result, this is our just definition. So maybe I'll write that at least, definition. So we just say they're independent if all of these occur. Now you might think, is all of this necessary? What if we just get rid of 4? I mean, if they're pairwise independent like this, then surely 4 would follow, right? Well, that's something to think about. So we'll do some examples in class and see if that's really the case or not. Likewise, maybe 4 is good enough and we don't need 1 through 3. So it would be good to think through a few examples and see why is this definition really necessary? And we'll do this in class. Now, we've done it for 2 events and we've done it for 3 events. It's a little bit more difficult to write if we want to talk about n events, but let's go ahead and try to do this. In fact, we could do it for a sequence, a countable sequence. So let A1, A2, A3, and so on be a sequence of events. So another way to write this sequence, it's a collection of events, or we can write it as a set. That is, well, we can write it this way. Let me do it in red or something to distinguish it. It's the collection AI such that I is a natural number, right? So remember, this natural numbers are the numbers 1, 2, 3, 4, 5, and so on. And then we can write this as AI such that I is some natural number. That gives us the set of all of these events. So we say the collection is independent if for every S contained in N, so every subset of the natural numbers, the probability of the intersection of AI's in the subset is equal to the product of the probabilities. Okay, so the notation is getting a little bit advanced here, I know. Let's do an example with a fixed S. So example. Essentially, this is just saying, well, so for 3 events, we could have taken the subset of all 3 things, or subsets of 2. Whereas if we only have 2 events, you only can take a subset of 2 to really mean anything. But now then, this is just saying a subset of any size, essentially. So say that S is the set 2, 4, 10, and 12, 13, I guess. So all this is saying is the probability of the intersection of all the events indexed in I. So that would be A sub 2 intersected with A sub 4 intersected with A sub 10 intersected with A sub 13. So that's all this notation means over here, is you just intersect all the events that have an index in the set S. And so here's our set S, and so we intersect over everything with that with those indices. And this is equal to, and now let's talk about the right-hand side. So this means you take the product over all these. So it's the probability of A2 times the probability of A4 times the probability of A10 times the probability of A13. So now again we go over every I in S, which would be 2, 4, 10, and 13, and we take the product of the probability of those sets. So it's the familiar thing that we just did. If we take a subcollection, here's a collection of the sets, A1, A2, A3, A4 up to infinity, then the probability of their intersection should be the product of the probabilities. And so that's all this fancy notation means. But that's what we mean by an independent collection of sets, is that no matter which subcollection you take, it satisfies this rule. The probability that all of them happen is the product of the probabilities that each one occurs. All right, well, God bless you guys. I'll see you soon.